This video is devoted to the cross product. This is going to be a short video and we're just going to cover the basics. Here's a natural question. If you have two vectors, can you multiply these vectors together? Of course you can take a vector u and a vector v and multiply them together in the sense of forming an inner product, which is typically the dot product. We do this all the time and we get a scalar. U dot v is a scalar. So let me rephrase the question slightly. Can we multiply two vectors together and get a vector as an answer? As long as we're in 3 dimensions, then the answer is yes, and that's the cross product. Indeed, given a vector u and a vector v, both of them living in R3, u cross v is going to represent a third vector that also lives in R3. Let's set up a bit of notation and define this with a formula. My vector u and my vector v that I'm going to be multiplying together, I'd like to represent in terms of the standard basis for R3. So I'm going to write out the vector u as u1, that's a scalar, times the first standard unit basis vector, plus u2, that's another scalar, times the second unit basis vector, plus the scalar u3 times the third standard unit basis vector. And for brevity, I'm going to use the notation I, j, and k to indicate those standard unit basis vectors. Let me also write v out as well so that I have the two expressions for u and v that I see here. I can now give you a formula for what the cross product is. First we'll look at the formula and then we'll talk about what it means. U cross v I am also going to write in terms of the standard unit basis for R3. So in particular I'm going to have a scalar, and a scalar sitting in front of I, j, and k, just as I had written out u and v. I'm going to write u cross v this way as well. And there's an explicit formula for what those three scalars are. The first scalar is u2v3 minus u3v2. The second scalar is negative u1v3 minus u3v1, and then that last scalar is u1v2 minus u2v1. Let me explain a really convenient way to remember this formula. A cross product is not a determinant because a determinant is a number, but a cross product can be calculated using determinants in a formal way, and they're conceptually related topics. We're going to calculate u cross v by working out something that looks a lot like the cofactor expansion for determinant. And in particular, we're going to be taking the formal determinant of the matrix that has as its entries I, j, and k in the first row, and then the coordinates of u and the coordinates of v for its second and third rows. So doing cofactor expansion along row 1, what we see is that we get I times the determinant of a smaller 2 by 2 matrix minus j times the determinant of a smaller 2 by 2 matrix and plus k times the determinant of a smaller 2 by 2 matrix. And now if you work out those 2 by 2 determinants, each of those is going to correspond to the terms that you see inside the parentheses. And those are the scalars that appeared in the formula for the cross product above. I personally find it much easier to remember calculating a determinant than memorizing a formula for the cross product. Let's now use this formula in an example. So I'm going to take two vectors, u and v, in this case 3i plus j minus 2k, and the vector v, which is I minus j plus k, and I'm going to work out what the cross product u cross v is. So I'm going to form my 3 by 3 matrix with I, j, and k in the top row, and I'm going to use my cofactor expansion along row 1. So I get I, and then 1 times 1 minus negative 2 times a negative 1, and minus j, times 3 times 1 minus negative 2 times 1 and k times another set of numbers. And that gives me minus I minus 5j minus 4k after I've simplified all of my formulas. If you like, you can plot these three vectors, u and v, and then the dashed purple vector is kind of pointing away from us, and this is u cross v, using the coordinates that you see in front of I, j, and k. I'd like to now observe something about this example. I'm going to take the vector that I calculated, u cross v, and take the dot product of that new vector with u, and also take the dot product of that new vector with v. This is just a simple dot product to work out, which I do here. And in both of these cases, I get 0 showing up. So is it a coincidence that the dot product of u and u cross v is equal to 0? No, it is not. In fact, this is always going to happen. In other words, the cross product is orthogonal to u and v. That's one of the geometric meanings of the cross product. Given a pair of vectors, you find a third vector which is mutually orthogonal to both of them. Now, the cross product, its properties, and doing calculations with the cross product usually comes up in calculus classes, and for many of you taking my class, you will have already seen and used the cross product in calculus. So we won't be spending too much time with it. We're just mentioning it in passing here. And so for the remainder of this really short video series, we're just going to go over some properties of the cross product and talk about the geometry of it just a little bit. Let's now discuss the properties of the cross product. First, u cross v is negative v cross u. This property, and actually most of them on this list, are quite easy to check just by using the definition directly. Here, if I think of getting that definition from the determinant, what happens if I interchange the row containing the coordinates of u and the row containing the coordinates of v? Well, that would change the determinant by a sign, and that's what you see happening in this first property. The second property tells you that cross product distributes over vector addition. The second property tells you how to do scalar multiplication, and in particular, a scalar times u cross v is equal to a scalar times u cross v. Notice that you don't put the scalar on both of the factors. This is also easy to check using the definition directly or by noting that this is related to the property of linearity in rows for determinant. Taking u cross the zero vector or taking u cross itself is going to give you 0. If you think about this in the context of our determinant, then having the same row here and here is naturally going to give you something that has determinant 0 because there's a linear dependency baked into the matrix. And then the last property deals with the dot product. And in particular, u dot v cross w is going to give you the same number as u cross v dotted with w. Remember that in a formula like this is going to give you a vector. And now you're taking the dot product of a vector and another vector, and so overall you're going to get a number. Likewise, on the right-hand side, this is going to give you a vector, and then the dot product of the vector u cross v with w gives you another number. So it wouldn't make sense to arrange the parentheses in such a way that you would have, say, u dot v inside of parentheses. It's also worth mentioning that the cross product is not transitive. Let's now review the geometric properties of the cross product. Most of these I'm going to assume you saw in your calculus class before this. The first is that u cross v is orthogonal to u and it's orthogonal to v. That's what we saw previously in the example. By construction, you have this orthogonality property. The second geometric property that's worth reviewing is that we can use the cross product to calculate the angle between u and v. Now remember, we can also calculate the angle between the vectors u and v with the dot product. In particular, the dot product of u and v is equal to the length of u times the length of v times the cosine of the angle between those vectors. Well, you also have a similar statement for the cross product, but it involves sine instead. The magnitude of u cross v is equal to the magnitude of u times the magnitude of v times sine of the angle theta between the vectors u and v. Let's think about what happens when u cross v gives us the 0 vector. This formula would tell us that 0 is equal to the length of u, whatever that is, the length of v, whatever that is, times sine of theta, provided that u and v are not actually the 0 vector. So for this equation to hold, that would mean that the sine of theta part would need to be equal to 0. So what angle has sine of theta equal to 0? Well, 0. So that means that u and v have no angle between them. They're parallel vectors. In other words, property 2 tells us that u and v are parallel if and only if the cross product is equal to 0. Next, let's relate the cross product to a formula for the area of the parallelogram spanned by u and v. Now, we already know that we can think of the area of this parallelogram as coming from a determinant. So it's reasonable that this might be related to cross product, which we also think about as being a kind of formal determinant. Let's now work out a formula for what that area should be. So we're trying to determine the area of the parallelogram spanned by the vector u, indicated in green, and the vector v, indicated in red. The base of this parallelogram is the length of u, and the formula for the area of a parallelogram is base times height. So we just need to figure out what the height is. There's a right angle triangle here as well, and the hypotenuse of that right angle triangle is v. So this is the length of v for the hypotenuse. The height of the parallelogram is the side that's opposite the angle theta. So since sine of theta is equal to opposite over hypotenuse, that means that the opposite that we're interested in, the purple line here, is going to be given by the length of v, that's the hypotenuse, times sine of theta. So this is the part that's the height of the parallelogram. Put all this together, and what do you get? You get that the area is the length of u, that's the base, times the length of v sine theta, that's the height. And by our formula above, that's the length of u cross v. Let's now work out one example. Let's find the area of the parallelogram spanned by the two specific vectors u and v given here. U is I minus j plus k, and v is minus 2j plus 2k. Our formula tells us that the area of that parallelogram is the magnitude of the cross product u cross v. And u cross v we can get with our formal determinant. By performing cofactor expansion along the first row of this formal matrix, I work out what the cross product ought to be, and I end up with a vector that has coordinates 0, -2, and -2, where I'm still using my IJK notation. That's the cross product, but to answer this question, I need a number, not a cross product, and so the last step is to take the length of that new vector. And that's just my usual formula for the length of a vector in R3, giving me 2√2 as the area of the parallelogram. So this wraps up our very brief review of the cross product. I'll mention that the cross product is very specific to R3. There is no analog in R2 or R4 or R5 or anything higher. So it's special to vectors in 3 dimensions.